Okay, thank you. Sorry for a technical issue, but thank you for the very generous introduction. It's really nice to join today. I'm going to share my screen and you'll all be able to see. Okay. Okay. So also, I'm going to share the link to these notes. So for today's session, I have just a couple of web pages. It's a little bit different from how I usually prepare these sort of tutorials, but we'll see how it goes. The idea, I just wanted to walk through a couple notes that I think cover the foundations of machine learning. And associated with each of these notes, you can just click on each one, right? I have a whole bunch of examples and a lot of pictures. And a lot of these pictures came from these notebooks. And if you're the kind that likes to learn by doing, if you like to just play around with some code, I have links to these Colab notebooks over here. You can feel free, open it, you can edit, you can play, and just get a sense of what it's really like concretely, right? So I encourage you to check it out. So it's not just you're listening to screen talking. Okay. Um, I guess we can get straight into it then. Um, so, okay, there are going to be three parts. Um, Actually, yeah, the main two parts I want to cover. One is how do we think about how do you set up a machine learning problem? Right? I think by this point, you've probably seen many algorithms. You've probably seen kind of in the abstract how kind of different machine learning AI ideas are set up. But I want to help see, you know, how do you take something that looks like, real world actual problem, and how can you translate that into a machine learning problem? And then the second kind of big question is there's so many different kinds of algorithms out there by now, right? It can almost be a little bit overwhelming. I've gone to some websites where it has like a list of data analysis tools for certain kind of data, and it was more than 1,000 tools. Right? So having some heuristics, some sort of techniques for comparing ideas, comparing models, that's really helpful. So hopefully we'll have a chance to discuss this as well. Okay, so let's get into this first part. Uh, so I think one thing that's often missing in a lot of the discussion for AI machine learning is people talk about it like you read about it in the news and it looks very exciting and it looks very kind of very distant from your everyday life. But then I remember at one point being just kind of struck by this thought that actually, even without any math, even without any computers, our subconscious is always making predictions, whether you realize it or not, right? I encourage you to step outside of the sessions, outside of what you're kind of trying to formally study. Just pay attention to how your mind works sometime and notice a couple times where, you know, you are making a prediction without realizing it, right? So he'll be a running example. It's a little bit of a silly example, but then it's something that I think everyone can kind of follow. Um, so imagine you're waiting at a bus stop and you want to know how long it will be before the bus arrives, right? Maybe this is not so relevant nowadays, but I remember a time before you had smartphone, before we could just look on Google and figure out when the next bus is going to arrive, right? You would really just show up and you'd have to kind of guess. You'd maybe know the approximate time it's supposed to arrive, but if it hasn't arrived, you might want to guess like, okay, how much longer am I going to be waiting here? And the way you do it is, nothing really formal, but then you'd be combining many different sources of evidence, right? There's no kind of one piece of information that totally tells you how long it's going to take. But, you know, I grew up near Los Angeles. It has a very famously bad public transit system. And you'd be able to use all these other kind of heuristics to figure out like how late might it be. Right? So it could be if the weather is really bad, if it's like very rainy, then it's usually late. If it's rush hour, also often late. And maybe like the best indicator was just how many people were waiting with you. If you were the only one there, maybe you missed the bus. Maybe your prediction is it arrived 10 minutes ago. But then if there's a lot of people waiting, then it's like, okay, maybe it's okay. So So you have all these kind of separate pieces of evidence. And now if we want to formalize this process, how do statisticians, how do machine learners begin to think about this? You try collecting it into a single vector, this xi, right? So D is the number of pieces of evidence that you're trying to combine to make your prediction. Xi collects all these different pieces. And then now you can imagine actually recording the amount of time you had to wait for a whole year, right? So these are like labels. These are data that you go out and deliberately collect. These are these YIs, right? And if I did this for a whole year, if I collected, number of people waiting at bus stop, current weather, and then how long I actually had to wait, then I get all these paired data and I get 365 examples. I've done it for a whole year, right? Now, at this point, you could imagine trying to ask a computer to learn this kind of decision rule or learn this kind of rule from all these pieces of evidence, what is the prediction, right? And the tools that the kind of algorithms that allow you to do this are called supervised learning methods. Okay. Now, this is pretty general, and a common distinction is worth making is the different kinds of inputs and outputs, right? What is the data type, right? So data type refers to if you have, like, the response could be very, very, could be any real number, which case is continuous. It could just be a couple categories, right? It could be just early, on time, or late. And then it becomes a classification problem, right? So this makes a big difference in the kinds of methods that are appropriate. You really should first check the data type, especially of the response, but you might also be curious. The data type of the inputs can also guide your decision about which methods to use. Okay, and there are many, many kinds of input-output data types, right? So, I listed it here as numerical input and numerical output, but you could imagine things like you convert one image to another image, or a bunch of numerical input into a whole function output, right? These all actually can fall into this general view of supervised learning. Okay. Before getting to the next point, are there any questions? I'd like this to be as interactive as possible. Okay. Okay. So let's get to, how do you actually solve this concretely? So first thing, supervised learning, you can think of it in a very geometric way, right? So I would think of the x, like there's a reason we use x and y in this notation, because you can think of x as like these inputs as like the x-axis on a graph. The response, y, is like the y-axis on the graph. And then the data that you've collected, right? Number of people at the stop versus wait time. You can plot out those data as points, and supervised learning problem is just learning the curve that kind of smooths out all those points, right? That would be if you only had one input, but really you could have many. And then it becomes like a multi-dimensional surface, right? So you can draw 3 dimensions, higher dimensions. It actually has a similar idea, but it's just harder to visualize. Okay. So that would be for continuous output. What if you have categorical output? You can do the same kind of geometric interpretation. Okay, so geometrically, what's going on here? Imagine this is the health example. So you're trying to say whether it's like a heart disease. You're trying to see whether different kinds of blood pressure and heart rate kind of variables are related to recovery from some disease. If I have only one input and my output is two classes, you could draw it as a real number line, so blood pressure, and then maybe the people with very low blood pressure are recovering. The people with higher blood pressure don't recover. It's not a perfect predictor because sometimes the colors overlap, but you can geometrically imagine it like a real number line and different colors. And again, you can do this in high dimensions. In this case, it's like you color in the prediction you would make for each combination of those two variables, and the observed data are the scatter plot points. Okay, So that's the next big, that's kind of the second big idea of this talk, is that uh, you can think about a lot of these supervised learning problems from a very geometric point of view, right? And this actually makes the problem sound very simple, right? Like all you need to do supervised learning, even these kind of very fancy image modeling and text modeling, is just drawing geometric curves in some high dimensional space. Like that sounds like a simple task, but it's actually kept the community busy for several decades. It's because it's actually a very difficult to execute, even though the idea is very simple. Right? So the way a lot of these techniques work is you define a model. What a model is a collection of these different curves or boundaries for classification. And you're trying to figure out which among that large class of curves is really good for the specific task. Yeah, okay. I see someone asking about the learning material. Let me give you the link again. Actually, do I have it? Yeah. Okay. So we need to go from this kind of very large collection of model potential curves or potential boundaries, and then find the right one. But then how do we even define the potential curves or the potential boundaries, right? Different models correspond to different sets of curves or different sets of boundaries. So let's look at an example, right? So you can imagine defining a whole bunch of curves just by having a whole bunch of lines, right? So the linear model family, these are kind of all the functions that are defined by an intercept, v0, so the intercept, and a slope, v1. So in this case, I'm drawing a line that fits through the data, but actually you can get any straight line using this formula. You could have like very low intercept, a large increase. It wouldn't fit the data well, but it would be actually belonging to this class f sub b. This is if you have only one input, you have slope and intercept. But the same idea works in higher dimensions, right? So it's intercept, and then you have slopes for each of the other variables. And in linear algebra, you might see this sort of longer equation represented by this transpose notation. So B transpose X in linear algebra just means it's like y equals mx plus b, kind of slope plus intercept, but then for all the different potential predictors. Okay. So in one dimension, it's just a line. In higher dimension, it's a plane. It's a hyperplane. Okay, so that defines a whole class of linear planes. How do you find one that actually fits the data, right? Like I've drawn it in a way that the lines actually go through the data, and here the plane goes through the data. But then in higher dimensions, you can't just visualize and try to guess. You can't just kind of manually fit these curves. So you had to do it in a sort of automatic way. So how can we do it in a sort of automatic way that the computer can help us? For this, you need something called a loss function, right? Let me just check here. Okay, so here's an example of a loss function for linear regression. Remember, n, it could be like 365, the number of days in the year for which you've collected data. Yi could be the amount of time that you're waiting. Xi could be all these predictors. And the idea is you want to be able to get, you want to choose B. That's why this is a function of B. You're optimizing over all the potential slopes. Like each different B is a different slope, a different intercept. So you're optimizing over all the different potential curves, and you're trying to get it so that they go through the data, which means that the distance from the prediction, this is B transpose X, is the curve is the prediction, and the truth, you want that to be small. Okay. So that would be for just continuous response. But then for categorical response, if you have different classes, like a recover or don't recover, here it's no longer a line, it's no longer a line, like a curve through some continuous space. Instead, you think of it as a linear boundary, right? So here I'm drawing this straight line to separate the two colors in this space, right? Now, how can you parameterize? How do you how do you define a set of these kind of linear boundaries in space? And a natural way to do it is to do this, to define this kind of logistic regression link function. Okay, so let's break this down. So this value is always between 0 and 1, right? So whenever it's smaller than half, you'll say it's the recover class. And whenever it's larger than half, you can say it's in the do not recover class, right? So whether you're closer to 0 or 1 can tell you which of the two classes you're in, right? And notice that this function, this denominator, gets larger and larger, and the more in line x is with b, right? So like if this exponent gets very, very large, then this denominator gets really large, and then this function gets close to 0, right? So the more aligned this is with the direction b, then the closer this function is to 0. And conversely, the more this is closer to negative infinity, right, then this exponentiation goes away, and you're just left with 1 divided by 1. Right? So then you can basically, by choosing your b and your x so that they're either close to infinity or negative infinity, then you can get the two classes that you want. Right? And actually, the direction of this line this is not obvious, but the direction of the line is exactly going to be the orthogonal to b, right? The reason is that moving in the direction that's kind of perpendicular to b doesn't change this at all, right? So you're left with the exact same probability all the way through. Okay, so we've seen linear regression. This here is logistic regression. Okay. So I see a question. The question is, sorry, what was the question? The question is, how do we explain the pink ball in the recover section, right? So this one, and the purple ball in the do not recover. Is this an error? So, the the question, if I understand correctly, is kind of thinking that, well, if this is really defining recover and do not recover, why would there ever be any kind of flipped colors, right? If I understand correctly. And the answer is that this model that we've defined is only an approximation to reality, right? The truth, the real world, doesn't actually have to match our model at all, right? So you can think that like this is actually like a mistake that our model makes because it's trying to be too simple, right? The real world might not have a linear decision boundary between recovery and do not, like recover and not, right? So in reality, maybe it's sort of curved, right? And you would still have to have some sort of mistake, but yeah, the model is only an approximation. The real world, there are all sorts of other little causes that might make someone recover or not, and we might not have even measured them all, right? So those things that we didn't measure that contribute to whether someone recovers or not, those show up as errors in our model. Okay, cool. And I encourage, if you have any questions, feel free to send in the chat or even just like unmute yourself and speak. I'm happy to discuss these. Okay. So we're left with the same issue as with linear regression, right? How do you choose this B? Like we could be pointing in any direction that we want. How do we choose a direction B that actually separates the two classes well? Before we use squared error loss, that works because the response is continuous, right? It makes sense to have, you know, any continuous value, you can just square it, and then it becomes some penalty, some positive penalty, right? But then how do you do that if you have only two outcomes, right? So here it doesn't really make sense to use a continuous, like a squared error loss anymore. The reason it doesn't really make sense is because like a difference, like an error of 0.01 probability, right? This might not mean too much when you're really close to one, right? But then it means more when you're near the boundary. right? So the probability, you shouldn't be thinking of the scaling as the same everywhere, right? Um, so you kind of need a different loss function. Yeah. Okay. And here's the loss function for logistic regression. Okay. So um, it looks a little bit complicated, right? So let's just break it down. So remember, yi in this context, yi is going to be either 0 or 1. It's like recovery or don't recover. F sub b, this is this function here. It's this probability logistic kind of function. It's all either between 0 or 1. Right? And okay, we have this form. It's actually pretty symmetrical if you analyze it, right? This is like y, and this is like the probability. So y times the log probability. And here's like a symmetrical version where it's just 1 minus y and 1 minus the probability. Right? So even though the expression is kind of long, the two pieces are kind of mirror images of each other. This one is like 1 minus of everything in the previous. Right? And they have the same essential form where it's like the truth log some prediction that comes from your function b, fb. Okay, so now that we've kind of understand the structure, what is its shape? What is the shape of this kind of loss function? Right. Okay, so let's imagine this. Imagine that the truth is 1, right? The yi is actually 1. And suppose that you predicted it with probability 1. So let's suppose your f sub b is 1 and the truth is also 1. What happens then? Okay, don't worry about this part for now. First, notice that if the truth is 1, then this entire second part goes away. Entire second part is 0. So we don't even need to worry about the second part. Only need to worry about the first part. Okay, and if it's 1 times log 1, well, what does log 1 look like? Right? Log 1, I just plot this into Google. So let's look at the blue curve. Log 1 is going to be here at 0, right? So actually, if the truth is 1, and you predicted with probability 1 that it was 1, then you don't get any loss at all. Your loss here is 0. The y-axis is 0, right? If you weren't so confident, if you thought it was only 0.8, right? Like you gave a 80% probability of the thing being 1, and it was actually 1, then you get a little bit of loss, right? Because this curve isn't exactly at 0 anymore. It's kind of down here. Maybe this is minus 0.15, right? So minus 0.15, and then I have a negative sign at the front. So the loss becomes 0.15, right? And kind of the more uncertain you are, you actually get a little bit of penalty. And yeah, you sum this over all the examples, all n examples. Okay. So any questions so far? And actually, I think I missed a question here. Okay, so there's one question already, and if you have others, feel free to add in the chat. But one question already is, how would the statistical distribution of the data inform the type of data modeling techniques to apply, since a simple model might not capture some complexities? Okay, there are many ways to answer this question. I think the first thing I'd say is, first, just make sure you understand the response type, right? So if you have continuous versus categorical versus count response type, this changes the kind of distribution that's plausible, right? Like if it's continuous, it kind of makes sense to use a Gaussian or maybe a Laplace distribution. If it's count, maybe you want to use a Poisson distribution, right? So just at the very outset, looking at the response type can tell you whether there's like a certain class of models to even consider. And then the second, more subtle thing you could do is actually make a lot of plots of the data, right? I don't think I have too many in this first lecture slide or lecture notes, but in some of the later ones, I showed just some example of just plots you can make. And by just getting a sense of which features and how they're related, you can either kind of define your own manual features, or you can deliberately choose a model that is designed for that kind of shape. Right? If you notice like a quadratic shape, you could use a quadratic regression. Right? If you notice a big step, like a jump, you can define a feature that captures that jump. Let me know if you have any follow-up question. Oh, Okay. And then I have another question here. Can you excel in machine learning with poor background in mathematics? And this is a
Hi,
private
Professor
question. So,
Kris.
uh-huh. Yeah. Hello. Hello. Any
Yes,
uh,
I just want to tell you that I have about 10 minutes so we could take questions
oh,
after. Yeah.
oh, okay. Sorry. I didn't realize. I thought it was extending off. Okay.
Okay.
Yeah. If you have follow-up questions, just send me an email. Um, I'll, my email is here. I'll type in the chat. Okay. So, actually, what I just described is kind of most of the theory that I was going to describe. And then I just wanted to give some concrete examples, right? So how do you actually do this in code? So here is how you do it using scikit-learn. So probably some of you have seen this, I'm sure. Uh, but the data set I'm looking at here is a diabetes data set. You're looking at whether the disease is progressing very rapidly or not too quickly, right? And then Uh, so what I'm doing here, this is just loading the data. So each row here is one person, each column is one feature. So one of the things that you might have tried to collect about them. And then here are all the different scores for how quickly or like how severe the disease is for these different people. Okay. So what does model do? Model defines this F sub B model collection, right? So it could work for any different direction, any different B. Okay. And then the next part, this fit, what does fit do? It goes to this loss function that we had defined above, this loss function, and then it just chooses the B that minimizes the loss function. So that's going to force the line to go straight through the data or as close to the data as it can go, right? And then here, these are the different slopes, essentially. So it's like an increase in the first feature by 1 unit will change the disease severity by this much. Right? So this is how you can get the output, the coefficients that come out. And so all that kind of abstract mathematical thing, it actually all just translates into code in this way. And actually, my answer for the person who was asking about mathematical background, I think you can build a lot of the same intuition that you would get from math by this sort of, you know, getting heuristic intuition about how these model and model fitting works in code. But I urge you to really pay attention to don't just like follow a tutorial, try to build your own intuition about how these functions work. Because at the end of the day, what the math is useful for is getting intuition about how the functions work. But if you can get that intuition through code, that can get you a lot of the way. Okay. And I have another example with logistic regression. So same idea, let's do the same exercise. This is a data set about, it's a fun data set. You're trying to predict the kind of species a penguin is from how its body shape is, right? So I have like the length of the bill, I have the depth of the bill. I think there are a couple other variables about like the wing, how long the wing is, how wide the wing is. So you have a whole bunch of these different variables about the penguins. You want to figure out which of the three species of penguin it is, right? Okay, and actually, I'm noticing there's a question about overfitting. I'm going to point people to notes about this. So I actually have a whole note on this, and I was hoping to get to it, but it doesn't seem like I'll get to it. But if you're interested in this overfitting question, here's some notes that kind of get into that whole issue. Okay, so, but let's just go through this practical example. Okay. So here I'm reading in this penguin data set, each row, a different penguin, and then I have these properties about each individual penguin, and I have the different species. So these are all Adelie penguin species. If you plot the raw data, here are just two of the features. You see something like this, where each point, sorry, each point is an individual penguin, and the colors are the different species. So remember before I was drawing these lines to separate the two classes? Here you can imagine drawing lines that separate the three classes, right? You imagine having a line out here to separate the dark green and the pink, you can imagine a line here to separate the light green and the dark green, right? So we should be able to draw linear boundaries. So this gives us some good reason for using logistic regression. Here, we're defining the model class and defining the features, the x, and the response, y. And I can just optimize the direction for these different separating lines using dot fit. Okay? And I can get the predictions, right? So, you can ignore this code. This is just for plotting it. But the true species, what is it? The true species is the color, and the predicted species is the panel in this plot. Right? So what you see is, the actual Adelees are usually put into the Adelie panel. So we get most of them correct, but we misclassify one of the Adelie penguins as chinstrap, two of them actually. And if you notice the ones that we misclassify, they tend to be the ones at the boundary, right? So the ones at the boundary are kind of ambiguous. Based just on the bill depth and bill length, they look like they could be either because they're near the boundary. Okay. And if you want an exercise, I have the code for this logistic regression in the Colab notebook. Try doing it with more than just these two predictors. If you want more of an exercise, see how the performance changes as you have more or less predictors. Okay. Okay, so actually, this is actually, yeah, let's wrap up with this. So we only really had a chance to talk about linear logistic regression. These were kind of my two most important though. So I have this at the very top of my diagram. But this is a diagram I use whenever I'm trying to just approach a brand new prediction problem, right? I am thinking about the different properties of the underlying data. First property, is the response continuous or not? So that would be blue is for continuous response, red would be for binary or like a categorical response. So the blue ones, these are both for continuous, red, these are both for categorical. And the purple you could do for either continuous or categorical, right? And then there's a notion called high dimensionality. We didn't get into it here, but the basic idea is if you have many, many, many features, more than just the two that I was showing you in some of the plots above, then you might want to do something more than just linear logistic. Right? There are these kind of four methods that all work in the high dimensional case. And if you are willing to assume that the boundaries are linear, then either of these two are work. Like the code for it, if you try the code in the Colab notebook, they're almost exactly the same as the code for what I just showed you. It's just most of the coefficients will end up being zero. So that it's basically like automatically choosing which features are relevant from the many large collection of features. But if you make a couple plots and you look and you notice that the response isn't really linear in the features, then I would start thinking about using some of these tree-based methods, right? So random forest XGBoost. Again, examples in the collab, these are going to be a lot more flexible if you're not able to make the assumption that everything is a linear boundary or a linear response. Okay. And just a couple more points about, what are the trade-offs between the methods? There is no one method that is optimal for all data sets. So understanding like which setting you're in can guide you towards the right method. Okay, so I think, I have some exercises below in case you want to test your understanding. But I think I'm ready to take any questions that people might have.
Question on direct message, and the question is, so the person is asking if he can do machine learning with poor background in mathematics. I guess that this person is just a beginner. So is it possible to do well in machine learning with poor background in mathematics?
Yeah. I mean, yeah, it's hard to say. Like, or I think I almost would not. I would not worry about it. Or I mean, it's I'm not sure how to answer because it's like on the one hand, I do really enjoy math, and I do really think that um, maybe not the specific mathematical concepts, but the patience that you learn by doing math does help in machine learning, right? Because there are going to be lots of times where some algorithm doesn't quite work, or reading a paper the first couple times around doesn't make sense, but then, the 10th time around it really does. I think that's a skill that I definitely picked up by doing math. But whether you actually need math to do machine learning, I don't think so, right? I think you need logic, and I think you need to be critical to be able to kind of look at your model and look at it very critically and say, when does it work? When does it not work? Right? But you can do that without math. And I think the way really to get good at it is to do some sort of hands-on, like really hands-on computational, like tinker with the algorithm itself, right? Um, yeah.
Okay, thank you so much for that. A beautiful answer. So some questions are just coming in now. So I think someone is asking, is there a way to choose a parameter to build or improve a model? Is
Yeah.
there a way to choose a parameter to build or improve a model? Yeah.
Okay. So, okay. There's two ways I'm thinking of it. The one way is there's within a specific set of models, right? So like in the kind of logistic regression example, right? Like there are many, many different directions you could have chosen to draw it. How do you pick the one direction to draw? Like the parameter here is B. How do you pick the B, right? And uh, for this part, it really comes down to this loss function, right? It's probably still not clear, or it's still not obvious for sure. But if you try playing around with different choices of B, like different directions for this separating line, the B's that make the most sense in terms of the data are going to have the lowest value of this function, right? Okay. And then the directions B, which have the kind of higher value of this function, tend to not separate the data well. That's one answer. Now, the second question you could ask there is like, I think this might be the question they were asking is like, how do you improve the model? A picture that I like to have in mind is like, let me draw this. Oh, why do I not see it? Um, okay, sorry. So like imagine the if you imagine a model as like you have some kind of complicated shape, right? And somehow like a perfect model is able to exactly remember this shape. A simple model, I think of it as like kind of getting a lot of it correct, but it's approximating it, right? So this triangle shape, it should be like my simple model, and the full curve is like the real thing, right? So what I might do is I'd fit that simple model, and then I'd look for the areas where it performs the worst, right? And then I imagine kind of you basically you analyze the errors, you look at the residual of a regression model, or you look at the misclassification for a classification model, and then you kind of figure out, okay, this is the reason it made the mistake. I'm going to add an extra feature, or I'm going to maybe add an extra penalty to my loss function that allows it to like extend the simple model with this additional piece that now it better approximates the more complicated thing, but it's still relatively simple, right? So this idea is called iterative structuration. That's like a fancy name, but it's basically just residual analysis. Like look at your residuals, look at your errors, and then build up your model from there. Okay.
All right, thank you so much. There are lots of other questions coming in, but at this point, we might need to really. So, if you have questions, so George, we're going to populate that and send it over to Professor Kris. So he's going to answer them. I will share it with the participants. So thank you so much, Prof. We are really super excited. Thank you for breaking down the foundations of machine learning in such a simplistic way. And I would like the participants to please appreciate Prof. Kris. Thank you so much. Thank you so